Alright, so this is going to be a video that basically shows the relationship between infinite limits and vertical asymptotes. So before we really start this, I kind of want to review what vertical asymptotes are. Now, a vertical asymptote is basically any time that you have a non-zero over zero. So I kind of wrote that here. We have a non-zero over zero for vertical asymptotes. So an example of that is if you had some function like y equals 1 over x. Okay, the vertical asymptote, if you notice the top right here is non-zero, that 1 is a non-zero, but this bottom, it's whenever it is 0, that is when a vertical asymptote is going to happen. So in this case, there would be a vertical asymptote at x equals 0. Okay, now to kind of show you this, I'm going to show you a graph that illustrates this point. So if we go to Desmos right here, I have graphed y equals 1 over x as such. And if you notice, there is a vertical asymptote at x equals 0. And I can actually graph it on here by doing x equals 0. And it kind of graphs it right there. And you can see the x equals 0 vertical asymptote. So again, it's anytime you have a non-zero over a 0. Now this is in contrast to holes, is where you have a 0 over 0. And that was kind of covered in a different video. So I'm not really going to worry about holes too much on this video. I'm going to be focusing on the vertical asymptotes and how it relates to infinite limits. Now this one was kind of easy. It was just probably the easiest example I could think of, where it's just 1 over x. I can change this non-zero up here. If I did something like y equals 2 over x, there would still be a vertical asymptote at x equals 0, because again you have a non-zero up here, and then at x equals 0 you have a non-zero over 0. Now again, to kind of show you that, I'm going to show you the graph. So all I'm going to do is change this value up here. It's 1 over x. I'm just going to change it to a 2. And if you notice, the graph changes slightly, but you still have that vertical asymptote at x equals 0. Okay, so again, it's that non-zero over 0. Now that is when x is equal to 0, so you can't change that obviously if you want. Let's look at another example. Say I did something where it was like y equals 3 over x minus 1. Okay, again, we have a non-zero up top, so I'm just going to write non here. Now on the bottom, to make this 0, this would have to be x equals 1, so that means that is where the vertical asymptote is to make that non-zero over 0. I'm going to graph this really quick to kind of show you. Okay, now if you look at this graph, if you notice the vertical asymptote, I graphed it as x equals 1. If you zoom out, you can see that the vertical asymptote is at x equals 1. All right, now that we reviewed vertical asymptotes real quick, now I'm going to talk more about what is actually happening at vertical asymptotes. So if you look at the graph right here, if you notice, we have one side right here that's going to positive infinity. It's getting closer and closer to that 1. The x is getting closer and closer to 1, but it's never actually reaching it. But the y, as it's getting closer to as it's getting closer to x equals 1, that y is going to infinity, and the opposite is happening right here. It's going to negative infinity. That infinity and negative infinity is really what makes vertical asymptotes interesting. If I was going to do a problem in which a value of x is getting infinitesimally closer to where a vertical asymptote is happening, there's only one of 3 things that could be happening for each problem. So what do I mean by that? Well, let's look at an example here. So let's take that last example that we just did and let's turn it into a limit problem. Let's go with orange. So let's say we have the limit as x gets closer to 1 for 3 over x minus 1. Okay, now if you just did direct substitution, you would have 3 over 0. Now again, that 3 over 0 is a non-zero over 0, so we know right here that our answer is going to be at a vertical asymptote, which means our possible answers for this, so let's just write that down, possible answers, they can either be infinity, negative infinity, or does not exist. Now, why could it be does not exist? Well, in this case, it actually is does not exist, because if we look at the graph right here, if you notice, as we're getting infinitesimally closer to 1, from one side it's going to positive infinity, from the other side it's going to negative infinity, so it doesn't actually agree on both sides. So for this particular case, the answer would be does not exist, because it doesn't agree on both sides. That makes it kind of easier because it doesn't agree on both sides. But what we could do is if we altered this problem a little bit, so let me alter this just a little bit. So we're going to have the limit as x gets closer to 1, and this time we're going to do 3 over, and this time in parentheses I'm going to write x minus 1 quantity squared. This is going to make our graph look a little bit different. So what I'm going to do is change this right here to put in parentheses, and then I'm going to make it quantity squared. Now if you notice, both sides, as it's approaching that vertical asymptote, they're both approaching infinity. So because of that, the answer for this one would be positive infinity. Going back to this graph, if I wanted to, I could have put a negative sign in front of this right here, and then it would be pointing downward, so you'd have negative infinity. So there is 3 possibilities that you can have for limits with vertical asymptotes. You can either have positive infinity, negative infinity, or does not exist. Now, this is for regular limits, not one-sided limits. With one-sided limits, it changes a little bit. So let's look at a one-sided limit for this particular problem. So basically, I'm just going to rewrite it right here. Now we're going to do, let's just say the limit as x gets closer to 1, and we're going to go from the right side. So I'll put a little plus sign right there, and we're going to do 3 over x minus 1. So I'm basically doing the same as this first problem we did right here. So the possible answers for one-sided could only be positive or negative infinity. So it can either be positive infinity or it can be negative infinity. It cannot be does not exist. The reason it cannot be does not exist because it approaches one value. We don't have to worry about approaching the same value on both sides because it's one-sided. We don't have to worry about each side. So in this case, let's look at 3 over x minus 1 as x approaches 1 from the right side. Okay, now we're only approaching from the right side. So if we actually approach from the right side, getting closer and closer to x equals 1, if you notice, it goes to positive infinity. So our answer for this problem would be positive infinity. So our answer for this particular problem would be positive infinity. Now, let's go the other way. So if we look at our graph from the left side this time, we are going further and further down to negative infinity. So because of that, if we're getting closer to negative infinity, the limit as x gets closer to 1 from the left side would be negative infinity. Now this is all great to do. It's great to show with the graphs. It's great to show that how everything makes sense. But what if you had to do this without a calculator? What if you had to do this algebraically? So basically these next steps I'm going to show you is how to do all of this algebraically. All right, so for this last part, I am going to show you how to do an infinite limit with vertical asymptotes problem, but I'm going to only this time I'm going to do it algebraically, so we're not going to use that graph to actually solve this. I'm going to show you how to figure it out algebraically just in case it is on a non-calculator part of the test, and I want you to kind of understand the logic behind it without the use of the graph. So first thing I'm going to do is write down the problem. So we already know the answer for this one. It does not exist because we did it before with the graph. So this time I'm just going to do it algebraically, even though we know the answer, just to kind of show you we get the same thing by the end of this whole thing. Okay, first thing I'm going to do, since it's a double-sided limit, I am going to break it up into two one-sided limits. So I'm going to do one side, and then I'm going to do the other. Now, the reason I want to break it down into one-sided limits is because we know one-sided limits at vertical asymptotes, they are either going to be positive infinity or they're going to be negative infinity. So I'm going to break it up by the sides for each side. Then after I'm done with that, if they match on both sides, then we know what the answer is going to be. If they match, it's just going to be whatever that value is if they match. If they don't match, then we know the answer is going to be does not exist. So I'm going to do this problem cold turkey. I'm going to act like I don't know the answer even though we already went over it, and hopefully this makes a little bit more sense. So I see a double-sided limit right here, a regular limit problem, and I notice that if I do direct substitution, it's a non-zero over 0, so I know that the answer could be positive infinity, negative infinity, or does not exist. So I'm going to break this down into, again, one-sided limits. So first thing I'm going to do is write down one side right here. So I'm going to do the right side here where it's 1 from the right side, and it's 3 over x minus 1. And then I'm going to do the same thing with the left side. All right, so I have both my limits right here. They're both one-sided based on this limit problem right here. Okay, now what I'm going to do first is, again, I can't use the graph, so I'm going to have to kind of use my logic and understanding of vertical asymptotes to answer this. So again, I know that if I plug this in directly, it's a non-zero over 0, so that means it's going to be positive or negative infinity because it's one-sided. But you need to figure out if it's positive or negative infinity. Now to do that, what you're going to want to do is substitute a value in. So we're looking at a value that is on the right side of the 1, so something like 1.1, 1.01, 1.001. Okay, and I'm just going to basically put that into this problem. Again, we know the answer is either positive or negative infinity. We just need to figure out if it's positive or if it's negative. So first thing I'm going to do here is I'm going to put this 3 down. I'm going to write it right here, and it's divided by, now I'm going to put a value that's on the right side of the 1, like 1.1 minus 1. Okay, the top, now all we care about is the signs because it's either positive infinity or negative infinity. So I'm going to care about the signs. The top is a positive, so I'm going to put a positive sign here. Now the bottom is going to be 1.1 minus 1, so that is also positive. So I'm going to put a positive here. Now positive over positive is going to be positive, so that means that it's going to be positive infinity. So this answer right here would be just infinity. Okay, I'll put a line here to kind of separate that. Okay, now I just plugged in a dummy number in here like 1.1. If you could see 1.1 is bigger than 1, so it's going to be positive. We have positive over positive equals positive infinity. That's how we get that answer. Okay, now we're going to do that same logic with this problem right here. So we're going to do 3 divided by, now x minus 1, but x is going to be on the left side of the 1 this time. So let's put some value in like 0.9. minus 1. Okay, again, we know the answer is either going to be positive infinity or negative infinity. All we need to do is figure out the sign. So the sign of that 3 on top is going to be positive, so I'm going to put a plus. On the bottom, it's going to be negative because 0.9 is smaller than 1. If you subtract that out, you're going to get negative answers. So we have positive over negative. That means our final answer here is going to be negative infinity. So because of that, this answer right here is going to be negative infinity. Okay, I'll put a line here to separate that as well. So if you see, based on what I have, we have positive infinity and negative infinity. So for one-sided limits at vertical asymptotes, it's really easy because all we have to do is plug in a dummy value. We have to go one step further if it's a regular limit that you have to care about both sides. If you notice, it's positive infinity and negative infinity. So that means this answer right here would be does not exist because the one-sided limits do not match on each side. So the answer for this would be does not exist. And that's basically how you want to do this algebraically. If there is a problem that's in a non-calculator part, you're not allowed to use your calculator, you're not allowed to graph it out or look at a table. So you can do this algebraically, and I basically just showed you how. So if you have any questions about anything in this video, let me know.